Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the Module 1 question from the Cape Chemistry, Unit 1, Paper 2, June 2024. Now, question 1A says that the figure below shows the electron transitions which occur between the energy levels in the hydrogen spectrum. So here's our figure, right? And if we look at the figure, we see that there are 7 energy levels, right, drawn on this figure. And what we see is that all of the arrows, right, are ending up at the n equal 1 energy level. So we have an electron that's falling down from 7 to 1, 6 to 1, 5 to 1, 4 to 1, 3 to 1, and 2 to 1. So this is a hydrogen emission spectrum. And so we're being asked to name the series of lines produced by these electron transitions. So when we have the electron falling down from all of these energy levels, right, where they were excited to previously, and then they fall back down to the n equal 1, we say that those series of lines are known as those in the Lyman series, okay? All right, so that's our answer here. Let's go ahead. So question 1B says draw diagrams including axes to show the shapes of the s and p orbitals. Okay, 2 marks. So here are our diagrams. So here's our s orbital. It's spherical as the s represents spherical. So we see that we have a sphere here, and that runs through the x-axis, the y-axis, and the z-axis. Remember, we're in 3D now, and so we show the z being this upright one here and the y being this diagonal. Now we look at the p orbitals, right? We remember that there are 3 p orbitals. We have a px orbital, and that one runs through the x-axis. We have a py orbital, and that's like this propeller shape. All of the p1s, as the p suggests, it's a propeller shape that it has. So it has like these 2 halves to it, and that runs through the y, so that's the py. And then the pz is going to run through your z-axis. Again, you have the 2 halves with the node in the middle at the origin. Okay? So you could either, for the 3p orbitals, you could either draw them separate, like I've shown them here, or you could just put them all on the same diagram, right? Showing one going in the x, then you have your y, then you have your z. So either way is fine, as long as you show that they have these 2 sides, the node is going through the origin, and you keep your axes consistent. That should be good for 2 marks, okay? So let's go ahead now to question 1, part C. So part C says, in methane, the carbon atom uses 4 electrons in hybridized orbitals to bond to 4 hydrogen atoms. What is meant by the term hybridization? 2 marks. So hybridization refers to the mixing of atomic orbitals to form what we call molecular orbitals with lower or intermediate energy states, right, than the energy of the atomic orbitals by themselves. So in the previous question, we had drawn the s and p orbital, right? So if you think about methane and the structure of methane, it's CH4. So this is methane, CH, 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 CH. And so what's happening in methane is that we have s orbitals on the hydrogen that mix with what are known as sp3 orbitals on the carbon themselves, okay? And so you may have seen this terminology before, but some more collectively what they would be within the realm of hybridization is that we would have sp3, that's when we have a single bond, right? And we can have sp2 whenever carbon is double bonded to something else. And then you would just see a sp if you have a triple bond. Okay, so here we see that they're all single bonds. So all of these bonds here that carbon has, they're sp3 hybrid orbitals, or they're molecular orbitals. So that's what hybridization means in a nutshell, right? It's these hybrid orbitals that would form when we mix the s and the p orbitals together to form orbitals of lower intermediate energy. So we don't need to draw this per se to get our 2 marks, but we have to be careful in how we explain it, that we're clear as to what's going on, that we're mixing atomic orbitals to form molecular orbitals, okay? All right, so let's go ahead now. All right, so part D says benzene exhibits resonance structures. What is meant by resonance? For 2 marks. So resonance is the phenomenon by which electrons can occupy 2 or more equivalent states. The molecular orbitals extend over 3 or more atoms, and as a result, it allows some of the electrons to move freely over these atoms. We say that these electrons are delocalized, okay? So this is a very comprehensive, detailed explanation of what resonance is. And so from a picture standpoint, since benzene was the example that they use, you will often see benzene in your textbook drawn like this, right? You have your benzene ring, right? And remember, there are conjugated double bonds around the benzene ring, right? So that's what benzene looks like. And so here we have double bond, single bond, double bond, single bond, double bond, single bond, right? So we said that benzene is conjugated. But the interesting thing to note here, when we're talking about resonance, what we're saying is that this double bond, guys, could potentially also be here. This one could also be down here. And this one could also be over here. And that form would look like this, right? Let me draw the shape again. All right, so the double bond that was previously here can be over here. This one could be down here, and then this one could be up here at the sides, right? So you see that, and then to go back to that state that we first drawn, this one could move back there, this one could move back down here, and then this one could move back over here. And so that's what we mean by resonance structure. So at any point in time, the electrons that make this double bond could move over to here and then make a double bond here. So they can run around the entire ring. And because they're free to roam about the ring, we say that they're delocalized, okay? So in any resonance structure, you will have delocalized electrons. So these are what they call the resonance, the various forms that are possible. And so very often what you'll see from a picture standpoint that represents, you know, the possibility that the electrons can be anywhere is you will see a ring, right? So that's how we generally represent benzene. It's like a ring instead of like showing the double bonds where they are, because in theory, they could be anywhere. So we just draw a ring. Okay? All right. So that's what we mean by resonance. So 1E says state 3 criteria used in the valence shell electron pair repulsion theory, so vsepr theory, to determine the shapes of molecules and ions, okay? So we're gonna have to really get into the fundamentals, the basis of vsepr theory to say how we're gonna use it to figure out the shapes of molecules, right? And so the first criteria in vsepr theory is that the molecular ion in question, right, will assume a shape where the repulsion between the valence shell electron pairs are at a minimum, right? Electrons are negatively charged. They're not going to want to be squished up against each other. So they're going to repel and go as far as they possibly can to minimize that repulsion. And that will dictate the shape. A lone pair repulsion. So if you have 2 lone pairs beside each other, they're going to repel a lot. If you have a bond pair and a lone pair beside each other, they're going to repel quite a lot too, but significantly less than if it was a lone pair beside a lone pair. If you have a bond pair and a bond pair beside each other, they're going to repel as well, but much less than if it were this or this. So you have to keep those things in mind. But fundamentally, what's going on is that electrons are charged, negatively charged species. They don't want to be beside each other, so they'll repel and go as far as they possibly can, and that will dictate the shape, right? And so with this as our basis, our base criteria, the next thing that we have to do then is count the number of electron pairs around the central atom in a molecule or ion. And then we're going to take note of any lone pairs present. So what does this mean? If we have to count number of electron pairs, it means that we're going to have to draw a Lewis structure, so showing the bonds that make up that molecule or that ion, and then count the electron pairs around the central atom, so the atom in the center, and then we're going to take note of any lone pairs present. Why we need to do this? Because lone pairs, as we said up here, have a lot of repulsion, so we have to think about how that might affect the shape overall. So that's the second criteria. And then thirdly, if we draw that structure of that molecule, that Lewis structure or that ion, and we see that there are triple bonds in there or double bonds in there, we have to treat that as a single bond. We're going to count that as just one single bond. Remember now, we're doing some counting, you know, as we said, from 2. And so if we see double bond, right? If we see double bonds, so say we have a double bond like that, we're going to count this guy as 1, and we're going to count this guy as 1. So we would say that around this carbon, there are 2 bonded pairs. Okay, instead of the 1, 2, you're not going to count them and say 4, you're going to say 2, because you count the double bonds as 1. So that would be 2 bonded pairs. Very, very important criteria here to note. Okay. All right, so let's go ahead now and see what else is being asked of us here. So it says use the criteria in E part 1 to determine the shape and bond angles in the beryllium chloride molecule. So that's the first one we're going to draw. So as I said, we are going to have to draw the structure, right, of beryllium chloride and then count how many electron pairs are around the central atom, look if there are any lone pairs, and then we can proceed from there, okay? Now, let's draw beryllium chloride. So beryllium has a valency of 2, and then, you know, chlorine has 7, right? And so if beryllium has 2 electrons that it can share, and chlorine only takes 1, because it's 7, it needs 1 to get to 8, then we're gonna have a beryllium atom that's sharing with that chlorine and another chlorine, so it can distribute the 2 that it has, okay? And so this is what we're gonna end up with, right? And let me just put in the electrons there. So I'm gonna use this pink one to be the one that's coming from beryllium, okay? Pink and X. And then I'm gonna use orange to represent what chlorine is contributing. So, you know, chlorine, around chlorine, you'd still have your others, your 6 that remained, okay? Okay, so it's 7, but we shared 1 with beryllium. And so that's why we only show 6 being on the chlorine. All right, and then beryllium now only had 2 and it shared its 2. So beryllium, when we look at this now, we see that beryllium is our central atom. Right, you see that? Beryllium is our central atom that we're gonna count the electron pairs around. Right? So when we look, we see that there's 1 electron pair here, and then there's another one here. So how many electron pairs are around that central atom? There are 2, specifically, they are bonded pairs, okay, or bond pairs. There are 2 bond pairs. As we say, we normally, after we count, we like to see if there are any lone pairs. There are no lone pairs around beryllium, right? So 1, 2 bonded pairs. No, when we have 2 bonded pairs around a central atom, right, you can consult your textbook on just the general shaped table. But whenever we have 2 bonded pairs around a central atom, those are they're bonded pairs, so they're still gonna repel each other. There's gonna be some repulsion, and they repel from each other in such a way that you end up with them being at a 180-degree angle to each other. So I'm going to draw that in here as the bond angle. Draw it here. All right, so that bond angle right there, you can see it's just a flat line. So that's a 180-degree bond angle. And when you have that, your shape is linear. Okay, so beryllium chloride is a linear molecule in geometry in its shape, and it has a 180-degree bond angle. Whenever you have two bonded pairs around a central atom, that's how they're going to organize themselves to minimize the repulsion. Okay, so we've applied our criteria that we discussed earlier here. All right, so that's beryllium chloride. So let's go ahead to part B of this. All right, so it says we have to use the same criteria established in part 1 to determine the shape and bond angle in the methyl anion. Okay, very important, the methyl anion. So for the methyl anion now, it looks something like this in terms of like the Lewis structure or the bonding structure, how we draw that picture of it, right? So we're gonna have our carbon. I'm gonna put carbon in pink. So we have our carbon. And then we have 3 hydrogens, as it says, right? H, H, H. However, we see that there's a negative charge on it, right? We see that there's a negative charge on it. So what does that mean? That means that the carbon has 2 more electrons than it normally would, or it has a lone pair on it, right? So we're gonna I'm gonna put those lone pairs on the carbon in orange here. Remember that normally carbon is tetravalent, so it would have 4 bonds coming from it. But because there are only 3 hydrogens, you're gonna have 1, 2, 3 bonds. And let me just put the electrons here as well, so we're being very consistent. Let me keep my colors consistent too. So I already put the lone pairs in orange. So I'm gonna use the bonded pair like that. And then I'm gonna put the electron that came from the hydrogen in green. So we're gonna do that on all of them. And then let's put the X from the carbon and the X from the carbon. Okay, so let's look at this now, right? As we said, because it's a methyl anion is negatively charged. Ordinarily, we would have 4 bonds coming from carbon, right? It has 4 valence electrons. That's what carbon has, right? And you know, hydrogen only has 1 out there in its outermost shell. And so here we are that we have 1, 2, 3 bonds that are there. And so there has to be a lone pair on the carbon. And how that would arise there is that if carbon, imagine that this carbon was bonded to a less electronegative element and it just grabbed an electron from that element, okay? Now we don't have to go through all of that detail, but we do have to know that there's a lone pair present on the carbon, okay? Because it's an anion, we know that there has to be an electron pair on it, okay? That's not bonded. All right. And so when we count, we're going to have to go around and count now how many electron pairs there are total, and then take into account the lone pair. So we're going to count now. We're going to count the lone pair as an electron pair. So it's 1, 2, 3, 4. So there are 4 electron pairs total. And in that, there is 1 lone pair, right? So remember what we said earlier, if we have a lone pair beside a bond pair, so let me write that there are 3 bond pairs so that we're very clear as to how that 4 breaks down, right? We said earlier, if there's a lone pair beside a bond pair, you're gonna have a lot of repulsion. Lone pair beside a bond pair, a lot of repulsion. And then the bond pair and the bond pair repel each other, but not quite as much as a lone pair and a bond pair would repel. And so what's gonna happen is that these lone pairs, they're gonna push the molecule down or push it down because of these bond pairs that are there. They don't want to be right beside them. And so in so doing, this is how the molecule is going to arrange itself. When we look at our table and we say, okay, we have 3 bond pairs and 1 lone pair, we look in that table tells us, okay, the shape that will give us is what is known as a trigonal pyramidal. And the bond angle for trigonal pyramidal will be 107 degrees. Okay? So that's how we would arrive at what the shape and the bond angles is for the methyl ion. Again, you're going to draw the Lewis structure and you're going to count up the electron pairs around it. There are 4 total. There's 1 lone pair. And so when you have 3 bonded pairs, right, and 1 lone pair, that gives you a trigonal pyramidal shape, and that has a bond angle of 107 degrees. Okay? So now we're going to move on to the next question. I'm going to move on to the next question. And it says that we are to draw a diagram to show the shape of the methyl anion. So I'm going to just take off the beryllium stuff and just keep what we have there for the methyl anion since we're going to have to draw the shape. It's just 1 mark, so it's just a simple, just a little extension of what we did previously. Just 1 mark, but we have to show the shape. So we have to show this trigonal pyramidal shape. All right, so let's do that. I'm going to just bring all of this up. Okay, so as we said, when we spoke about our criteria, really what's going on is that the electron pairs are trying to minimize repulsion in the molecule, and that's what dictates their shape. So what we said is that if we have a lone pair beside a bonded pair, that's going to be a lot of repulsion, much more than if the bonded pair is beside another bonded pair. So what we can do is we can squish this hydrogen. This lone pair is going to push this hydrogen down, right, to get the minimal repulsion in that molecule as a whole. And so when we look at it from a shape standpoint, we would draw, we're going to put the carbon up here, right? And then that lone pair, I'm gonna draw the lone pair there, right? And say this lone pair, this is the guy who is causing the shape to be what it is. And so the hydrogen is gonna come like this. It's gonna be down here. This has to stay. This is the bond. This is representative of our bond, this bond pair. It's gonna have to go away from it. So you see how up here I had it beside it like on a flat line right there. No, it has to push down. The lone pair will push it down, right? And then we have this hydrogen here. I'm gonna just put that one there. Remember we said bond pair repulsion is not as strong. Still repulsion, but not as strong. So they're gonna be in that proximity to each other. And then we're gonna have this hydrogen, this one. Again, the lone pair is gonna squish him down. So it's gonna go down as well, okay? And so with that's how we end up getting the trigonal pyramidal shape. So let me just kind of sketch out what that trigonal pyramidal structure will look like, right? And then show the bond angle of 107 that we said it would have. So I'm gonna use a different color now. So let's use this green here. Actually, let me use this blue here, right? So generally, when we're just like sketching out the shape, we just draw the vertices. And so I'm gonna draw this bond, connecting to that bond, connecting to that bond, and then connect these two there. And then we're gonna just go up here to the lone pairs. And then of course, that one would have to come down here. And then this hydrogen connects to, and then this hydrogen connects up here to that lone pair. And so this in here is our base, right? Or triangular base there. So this is how we draw that triagonal pyramidal shape. And then our bond angle now, let me put that bond angle in purple. So that bond angle, that 107 would be between these, okay? So that is your 107 degrees bond angle. Okay, so remember, all we're doing to figure out what the shapes will be is we're applying our criteria. We know that fundamentally, the electrons are going to arrange to minimize repulsion. We're going to draw our Lewis structure. We're going to count everybody around it, what the number of electron pairs are. We're going to say, okay, are there any lone pairs? Because we know that those repel a little bit more than the others. And then we can consult our table that we should have in our minds at this point and see, okay, if there are 3 bonded pairs and 1 lone pair, I'm going to get a trigonal pyramidal shape with bond angle 107. And you can always just sketch that out like I just showed here. Okay? And so with that, we've come to the end of this part of the module 1 question. Definitely give this video a like, subscribe to the channel, and if you look on your left here, you'll see the next video up. And if you look on the right here, you'll find our Module 1 playlist with tons of interesting content that will be helpful in getting you prepared for your exam. So thanks for watching, and we'll see you in our next video.